Hello everybody, welcome back. It's 10 minutes later, I'm done mewing, my jawline pristine, and today we're going to be talking about Apache Iceberg. Now this is something that I guess I had a very high level understanding of, and it's probably good that I went ahead and got a more low level understanding of it. Now for what it's worth, I'm ripping a lot of this off of just existing YouTube content, specifically from one guy named Alex Merced, so I'm going to link a bunch of his stuff because it was actually very useful for making this video, and I don't want him to be mad at me because that would be wrong. Anyways, let's go ahead and talk about it. Alright, so Iceberg is a project that I guess is open source, but technically it was kind of run by Tabular, the company, which got sold to Databricks, so a lot going on there. But I guess the gist is that Iceberg is ultimately what's known as a table format. So you might be wondering, well, what is a table format? Well, I guess we're going to go through the history there and the etymology of the word and what it really means. So it's going to allow a lot of interoperability, basically just modularity, between a bunch of storage and compute layers. So if you recall from our Snowflake video, I guess the new meta of big data lakehouses is you want your storage layer, typically S3, and you want your compute layer. And that's going to differ quite a bit, but generally speaking, those are decoupled, and being able to kind of replace them and choose one or another and kind of switch them out easily is very, very important, and Iceberg's going to help us do that. Additionally, compared to something like Apache Hive, which we'll talk about in a little bit, or the Hive Metastore specifically, it's going to offer both a lot of performance and consistency benefits, which is going to make dealing with these massive tables quite a bit easier. So the first thing that we're going to do is discuss the term data lakehouse, because this is something that probably up until this point really was something that I understood at a high level, but I guess was kind of just a buzzword for me, and I didn't really understand what it meant empirically, and I guess now more so I do. So data lakehouse, I guess, obviously by the name, is in contrast to the data warehouse. So in the data warehouse, we've got a bunch of data sources. They're publishing to some sort of data lake, which is S3. And this is a data lake because I guess the gist is that you just dump a bunch of stuff in there. I'm not going to make that a sexual joke. I'm going to choose not to today. Dump a bunch of stuff in your data lake, and then from there you run a bunch of ETL jobs, extract, transform, load. So basically just batch jobs, could be Spark, could be MapReduce, anything like that. And take them and put them into a data warehouse. Now, traditionally, the data warehouse is some sort of major SQL table, right? You might use that Snowflake or stars and Snowflake schema that we've spoken about in our concept series. And typically, in the past, this would have been some expensive custom hardware, maybe Oracle or something like that. Who knows? But the point is, if you want to scale it, you're kind of at the whim of the database that you chose, and ultimately, you're having a lot of platform lock-in, and this is going to be expensive. On the contrary, the data lakehouse, I guess, in theory, is going to be using as much open source technology as possible, or not necessarily even that, but the gist is you have a data lake, right? You store your data once, and then from there you query it directly within the data lake by using a separate compute layer. So this compute layer is something that you've got a bunch of different competing engines that can all be doing it and all have their own pros and cons. But the gist is here, it's cheap, it's scalable, it doesn't require you to lock yourself into custom hardware. And when you use this in conjunction with a technology like Apache Iceberg, you can easily switch them in and out which one that you're using. Cool. So what is a table really in a data lakehouse or something like that? Well, a table is just going to be a collection of a bunch of associated files, right? So we've got a bunch of files in S3, and the question is, well, how do we know which files are actually associated with which table? I guess the gist there is you have to keep some mapping between them, right? So for example, we've got table 1 comprises of these top left 3 files, and table 2 might comprise of these bottom right 3 files. And so I guess the gist is, right, if you have a bunch of different compute layers running, maybe one team chose to use Spark for whatever reason, one team's using Dremio, one team's using Presto. These are all ones that we're going to talk about later, but it's not really important how they work right now. The gist is they're different. They all need a way of basically figuring out, okay, well, I understand that regardless of what compute engine I am, I know which files belong to which tables or which partitions of each table. Cool, so let's actually talk about this concept of a table format in general. A table format is basically just going to say, hey, we have a bunch of files, the table is an abstraction over these files. How do we kind of take these files and map them out into our table extraction? And the way that we do that is, well, our table format is going to expose to us which files exist in the table, and more importantly, not just within a table, but also within an actual partition, right? Because splitting our table into partitions allows us to do a lot of pruning and pre-filtering without actually having to read a bunch of files. And also, which partitions are actually in the table itself. And then possibly more data than that as well. It depends on the table format. It's great if there's more data that we can get out of this because it means we can build on more features and it might help us with our performance. Cool. And the gist is, if we can all kind of understand the same table format, or we're all, expressing some additional data in the same way about these files in S3, then we can kind of switch in and out what storage system that we're using, or potentially also which, compute system that we're using for actually doing the querying. Cool. So I guess one thing to touch upon now for historical reasons here is going to be Apache Hive. So Hive is basically important for a couple of reasons. For one, it's basically a SQL wrapper around MapReduce, where you'll give it a SQL script and it'll convert it into a MapReduce job, which itself is super useful because there are a lot of people who know how to write SQL queries but don't really know how to write Java programs, and that's quite important. And number two is that basically as a way of getting this done, they introduce something known as the Hive Metastore. And the Hive Metastore is basically listing out all of the files that comprise a particular table, so that the SQL queries can actually be translated into Java programs to actually go ahead and run these queries. And so the idea here is that in this kind of Hive table format that we have to use, the way things are done is maybe you'll have a list of tables, or this is going to be directories within Hadoop, right? You've got your root directory, maybe you've got a tables directory, one table called Jordan's DMs, and then from there we've got a bunch of partitions, one per date ID. So January 1st, January 2nd, January 3rd, January 4th. And each partition is basically stored as a folder. And within one of these folders, maybe we've got a bunch of different files. But at least within the Hive Metastore, which you can think of as basically a separate database listing out all of the directory names, we aren't actually storing any file names. We're just storing the directory names, which is effectively just telling us what partitions exist. So Hive has a few pitfalls, which, despite its popularity, ultimately made it, become much more extinct than it was at some point. So basically, like I mentioned, Hive is only listing in its Metastore a bunch of partition directories. And so if we only have the directories, that means on each query we have to go into each directory in our actual storage layer and run an ls command, right? So an ls is listing all of the files in that subdirectory. And so if we have to do that, basically, let's say we're reading from 10 partitions, we have to read 10 ls subcommands. And if there are a lot of small files in there, that can actually be a pretty expensive command, and it can take a lot of time to execute that. And so the actual planning phase of the query could take a super long amount of time, even if the query itself wasn't that expensive for whatever reason. Additionally, in the Hive Metastore, all of the writing was done using locking. And so when you're using locking and then all the reads rely on the same metastore to actually figure out what files they have to read, or what partitions they have to read from, rather, now all of a sudden your writes and reads are going to interfere with one another, and that's going to be a bit of a problem. So we don't want to be blocking read operations, generally speaking, because the entire point of these databases is basically to have as slow as tolerable writes and then as fast as possible reads, because the reading case is going to be the common one here, at least for analytical workloads. Cool. In terms of correctness, basically Hive metastores also were pretty poor when it comes to atomicity. Basically, a bunch of things could lead to partial failures. So examples of those would be like renaming columns, adding and dropping partitions, moving files from one partition to another. Basically, I think it's possible that depending on the implementation of the metastore, this is somewhat resolved. But just due to the fact that you've got all of these directories in Hadoop, and then also you're keeping the directories separately, basically duplicating that data over in the metastore, it's going to be pretty darn hard to keep those two consistent, because they're just different machines on the network, and so you always run into the possibility of having partial failures, which is quite bad. Cool. So what is Iceberg really? Well, it actually, on a surface level, does look kind of similar to that Hive table format, but we'll see that there are some differences. So for number one, Hive is itself just a table format, right? Like there's no database associated with it that is going to, or sorry, not Hive, but Iceberg is itself just a table format. There's no database that is returning you all of this metadata that we're storing about the table, at least not native to Iceberg. Now there are things called catalogs, and these are different projects that are basically responsible for serving Iceberg data. But for now, let's just talk about the format. So like I said, we've got some data. It's served by something known as a catalog. And basically, it looks something like this. At a high level, it's, here are partitions for a given table. Here are the files that they contain. Here are the schemas of our table, or the schema of our table. So we've got a bunch of date, string, and int columns, and we've got the names associated with them. So what you might notice is right off the bat, because this schema is in metadata, it makes things like renaming a column super easy. It makes things like casting a column to a different type at read time super easy, because we just know to do that from metadata. And all of these engines, of course, can basically get their hands on this Iceberg format, and then they can go access the underlying files as necessary. Now, another thing about this, or a problem that I mentioned with Hive and kind of how Iceberg deals with that, is two ways. One is that note that we've explicitly listed out all of the file names in a partition, so we don't have to go down to S3 and say, hey, S3, return me the result of this ls query. And then number two is that we use copy on write semantics. Copy on write basically means if I want to modify this metadata state right here, I can do so, but I basically have to copy it. During that time, any reads can be served from the old metadata state, and then I write out my new state, and then atomically I switch over the pointer from the old metadata state to the new metadata state. So that's going to keep all of our writes atomic as well. So pretty much already based off this one simple design trick, or I guess a couple simple design tricks, we have pretty much mitigated all the major flaws of Hive. So let's go over to this architecture in a little bit more detail. So number one, like I said, the fact that we're explicitly listing files helps us avoid extra calls to our underlying file store, which are going to be slow. Number two is that all the metadata is updated with copy on write. All of our files are immutable. This is just how things are in object stores in general. So even though in HDFS you can append files, in S3 you cannot. And so as a result of that, we're basically just going to always deal with immutable files. We're never going to append. So this is going to make sure that writes don't block our reads, and that's going to be very important because reads are the case that we really, really want to optimize for, generally speaking. Number two is that state is going to be updated atomically, right? If I have a pointer in my kind of catalog database from a table name to its Iceberg metadata, then all I have to do is basically just change the pointer to our new version of the Iceberg metadata, and I'm good to go. As a result of that, if I keep, if I keep the file around that corresponded to the old version of the table, now I can do this concept of time traveling, right? Where I can look at the previous schemas or the versions of the database and read the database using that previous schema to kind of get a sense of what it looked like in the past. And then also, because of the fact that our metadata is including things like schema and partition information, doing those operations that weren't atomic using the Hive metastore now become atomic because, again, basically committing something or making it visible to all of our query engines is really just switching over that pointer, which is a one-time operation in our Hive catalog or in our Iceberg catalog, and then we're good to go. Cool. So the one thing to note is that copy on write semantics do kind of make our metadata changes a little bit expensive. How do we go ahead and optimize that, right? Because when you're doing a copy on write, if it's a very, very big file, which is going to be the case for gigantic tables, we've got a lot of files in there. It's going to be hard to do that copy and then do the write, and all of our write operations are going to be super expensive. So what can we do? Well, basically what we do in Iceberg is we have this concept of like a metadata hierarchy, right? So what does this really look like zoomed in? Basically, to start, we've got our catalog, which is basically a mapping of table to the file that contains its metadata. So we've just got one of those, and again, that's going to ensure that we can atomically flip over to a new version of metadata at a time. Now, all of these files that I have listed out, they're probably going to be put in our object store somewhere, like S3. So that is worth noting. So we've got our metadata file right here, which is basically going to have like a UUID for the table. It's going to have our schema listed out. It's going to basically say how we're partitioning our table. So in this case, it might be, by date ID or something like that. It's going to have the current snapshot ID. So a snapshot is basically representing the current metadata for the table. So keep in mind that this metadata file is not actually storing the snapshot data itself. It's basically just saying here is what the current snapshot is. And then it's going to have a list of all the snapshots where every single snapshot has a file in S3 associated with it. And this is, again, going to allow us to do easy time travel operations. So basically, each one of those snapshots is pointing to something known as a manifest list. So think of the manifest list as like, state of table at some point in time. Note that we also have our old manifest list right over here. We may not be actively using it at the moment, but it's good to keep it around in the event that we want to reference it in the future. So what does our manifest list actually contain? Well, it contains the following things. It's got a list of partitions and their corresponding manifest file. You can see now that we're starting to have a bit of a hierarchy of our metadata here in the sense that, we're basically splitting up our partitions such that one manifest file can contain multiple partitions, but we can have many different manifest files. Cool. And then that is going to basically be, storing the metadata for those partitions. So one nice thing about this is because we have this list of partitions in our manifest list, we can do some amount of pruning here, or data pruning. Because let's say our partitions are broken down by date ID, and I only care about the data in one date ID, I can basically say off the bat, I only need to contact the manifest for that particular partition. Cool, so let's move on. Now we're at the manifest, which is going to have data for, I guess, one or more partitions. Cool. So within a manifest, the data that we contain, or what we're holding in here, is basically the list of partitions that it's responsible for, and the associated data files within each partition. Keep in mind, one partition can still have many data files in it. Another thing that we need to know is the actual format of the data file, because Iceberg does work with many data formats, right? You could maybe be using Avro, maybe you're using Parquet, maybe you're using CSV. We're format agnostic, which is great. And so we have to list out the actual format so that we know how to read it. And of course, the associated file level metadata. So the interesting thing about the file level metadata here is it's very similar to the metadata that we've spoken about in Parquet in the past. So in Parquet, basically the metadata is stored at a row group level. Keep in mind that in Parquet, basically what you'll have is a subset of rows will be stored contiguously, and within that block, basically all of the data within the same columns is stored contiguously. So you'll get metadata for that row group, maybe like a min and a max and the number of nulls or something like that. But in this actual manifest, it'll do that on the level of the entire data file. And so this is actually going to potentially allow us to even skip reading the row group itself to actually go into its header area in Parquet and get that metadata. This is going to potentially save us some more reads. So this is something that Hive does not do. So again, we're actually doing file level pruning here, as opposed to just row group level pruning that we might be doing in Parquet. Another nice thing about this is that we've also got some metrics for each file for cost-based query optimization. So maybe the number of rows, things like that, to get a sense of how expensive a scan would be if we're going to scan a certain amount of data. And that's good for our query optimizer to ultimately make the best plan possible. So another nice thing about that is, as opposed to Hive, which basically will, pull the data and every once in a while update these metrics for optimizations, this guy is going to be updated every single time that we write new data, which is going to keep it up to date and ideally keep our queries as optimized as possible. And then finally, I guess the last piece of this is going to be the fact that we've got our actual data files over here. So these are just going to be Parquet, CSV, Avro files, but the gist is the manifest has pointers to those as well. And so when we eventually read all of this Iceberg data in our executor nodes to get a sense of where we have to read, well, finally, of course, we're going to actually have to go ahead and read some data itself. Alrighty, my camera just crapped out on me, so we're back at this. But basically, the last topic that I want to cover here is the copy on write versus the merge on read semantics. So when it comes to data files in our Iceberg tables, they should all be immutable. In fact, they have to be immutable. S3 doesn't even support appending files, so assuming you're using S3, which you probably are, it's going to be immutable. If you're using HDFS, I guess in theory you can append files, but in Iceberg tables you can't, so don't do that. Basically, this is going to give us two options to go ahead and update our table data. Number one is going to be copy on write. We've discussed this a bit. If you have 1,000 rows in your file and you want to update one of them, you basically have to copy that entire 1,000 row file, update the one row, and then atomically replace it by updating your metadata state. So that's fine in the sense that reads are now going to continue to be fast because all your files are still immutable and there's nothing to really worry about there, but writes are going to be super slow. If you do want to speed up writes, which probably is often not going to be the common case with analytical workloads, at least compared to optimizing for read speeds, what you could do is use merge on read semantics. So basically the gist is here, if I want to write over 1 in 1,000 rows, instead of overwriting the entire file and having to copy it, what we can do is just keep track of the overwritten rows, and then at read time actually merge in the new values. And so this is going to make our writes faster, but our reads a little bit slower. So the question becomes, well, how do we actually keep track of these overwritten rows? And Iceberg supports two ways of doing so. One is going to be position deletes, one is going to be called equality deletes. So in position deletes, we basically take all of our explicit row numbers, or perhaps more accurately there, actually just the addresses on disk, that were actually overwritten. And the way that we would do that is basically as we actually write data, we have to go ahead and read the file that contains the old row that's being overwritten, and then we have to go ahead and keep that in some supplemental position delete file, right? So in this case, note how Jordan and Corinna are being moved to married at the same time. Odd coincidence. I don't know if they're related, but correlation doesn't imply causation, as they say, but in this case they might be related. As you can see, all of a sudden row 1 and row 4 have been overwritten, and so we know that if we read this file, we have to check our incremental updates file to actually get the new value for these rows. So there's going to be a little bit more work on the read path as well. As far as equality deletes go, same idea, but basically the gist is, instead of explicitly listing out the row IDs where we have overwritten data, this time we don't have to actually read this file when we overwrite certain rows of it, or we don't have to read the entirety of it. The reason being, we just keep track of the actual predicate itself. So in this case, let's say our query was in fact overwrite the status of Jordan and Corinna to be single, or to be married. I would basically keep track of that predicate right here. So we're going to basically say we have to merge in all rows where the name is in Jordan or Corinna. And so as we're reading through this file and actually returning the rows of it, we can then say, oh, you know what, I see this row, I've got a value that I got to overwrite for it. Same for this row, let me go ahead and do that. So of course this is going to lead to more work being done on the actual read path to evaluate the predicates. Now as time goes on, these guys are just going to get bigger and bigger and bigger, and they're going to get more expensive to deal with. So of course, performing some amount of compaction in the background is going to be the best thing for us, because basically when we compact these files, the overwritten data will get removed and replaced with the proper values, and then we can get rid of all of these extra predicates or all of these extra position deletes that we have to deal with. Okay, in conclusion, table formats initially seem like they're probably only going to be useful for interoperability, right? Like, it's very nice to have these because it means you can use multiple different types of compute, multiple different types of storage as well. However, they actually do have very important implications or ramifications depending on their design, right? Like, it's very easy for Hive to become a bottleneck in a particular query, and that's basically what ultimately led to the creation of Iceberg. And so you can see how Iceberg kind of really tried to shape its design around not screwing with concurrent writes, or rather concurrent reads, whenever you're making a write, and also being sure to basically just allow us to have good ACID guarantees as well, so that we can make sure that we're updating our data safely and not dealing with all these partial failure scenarios. Anyways, guys, I hope you enjoyed this video. Iceberg's a pretty cool topic, and it's a fairly new technology, so I'm very excited to see where it goes.